post. Sign up for a contributed talk. So, parabéns, Iara, but shame on you. Okay, so just a second, we get the batteries for the microphone. And tomorrow, for those of you who need to print the poster here, tomorrow, be around tomorrow just after Mac's lecture, so at 10:30. Somebody will take you to somewhere where you can print the poster. Maybe you have to pay something. Yes, bring some money. I have no idea how much will it. Do you know how much will be the poster? 3 reais per? No, 37 reais for a one page. Yeah, I mean, a poster is on paper. Yes, what do you mean? Ah, okay. Okay, it's around 40 reais. Okay, so we have Iara's talk, and then we stay here for the discussion with the speakers. Yes. Okay, please.
Good afternoon. My name is Iara. I'm doing a PhD, and my PhD advisor is Cecilia Crente at University of ABC. Today I'm talking about a work we named Analyzing the Overtones in the Ringdown of Binary Black Hole Mergers. So as we know, in 2015, the first detection of gravitational wave happened, and this opened a new era of gravitational wave astronomy. With gravitational wave, we can detect things we could not with electromagnetic radiation. For example, we can know better about the black hole and neutron star population in the universe. We could learn something more about neutron star matter, because by this time we don't know exactly the equation of states of neutron stars. We expect to detect cosmological signals, for example, signals from dark matter or from the Big Bang. With gravitational wave emitted in extreme condition of gravity, we could use to test the nonlinear regime of general relativity. So, for example, binary black hole merger are in this nonlinear regime, and we could detect unexpected signs. So we could learn more physics about it. So here I'm going to talk about tests in the general relativity. LIGO is been running since 2015, and in the first run it detected 3 black hole mergers. In the second run it detected 7 black hole mergers and 1 neutron star merger. And the third run, which is started in April, is detecting approximately 1 black hole merger per week and 1 neutron star merger per month. That's approximately that. So I'm going to talk a little bit about the black hole mergers, the gravitational wave emitted in black hole binary merger. So it passes through 3 stages, which we call spiral, merger, and ringdown. The spiral phase, the black holes are orbiting each other in a near Keplerian orbit, and they are losing gravitational energy through gravitational waves. And this part of the wave is described by post-Newtonian approximation, which is a linear theory. But when the black holes get really close together and they get really fast, the linear regime is not valid anymore, then we need numerical relativity. So it's between getting in the merger, and after the merger, the black hole acts like a perturbed black hole. And here I'm going to talk about the last phase of the gravitational wave, which needs the black hole perturbation theory. So I'm going to talk a little bit about the black hole perturbation theory. When you perturb a black hole, it passes through 3 stages. The first stage is called transient, and it depends all on the initial perturbation. So it depends in this part. You can see in this part near from 0 to times 70. Here is the time is measured in mass. The unit is mass, it's not seconds. And this part of the wave here depends only on the initial perturbation. That's just an example. The second part of the waves are called quasinormal modes, and the waves has characteristic frequency of oscillation and a damping time. So the wave is here in the example, in the time between 50 m and approximately 20 to 200, we can see a damping oscillation. It's decaying exponentially here, and we can see clear the characteristic frequency of oscillation here. Here is less clear, but here until 2000 we have the oscillation and the quasi-normal modes, and after the quasi-normal modes we have the power law and the oscillation cease. So I'm interested in the quasi-normal mode because this damping time and frequency of oscillation depends only on the black hole properties. So for astrophysical black hole depends only on the mass and the spin of the black hole. That's why I'm interested in this part. And the quasi-normal modes are also seen in the final phase of the binary black hole merger. So why do we call it quasi-normal modes? We learn a lot of normal mode in physics, and a wave can be written proportional to of I omega t, or omega here is a frequency. And in the normal mode case, we have a closed system. So in a closed system, we have to set boundaries, and the waves vanish at the boundary. And when we set this boundary, the waves vanishing in the boundary, it turned out that this omega frequency is a real frequency. So we're going to have a constant oscillation, like this one picture here. So the oscillation won't decay. But in the case of a black hole, we have a system. It's open in the event horizon, and the wave can go to infinity. So we cannot set the wave to vanish in the boundary. You have to set another more physical boundary condition. And in this case, we're going to say that no wave can, we know that a wave can be written as a linear combination of a left-going wave and a right-going wave. And we're going to say that no wave can leave the event horizon. That's a physical condition. Nothing can leave the event horizon. And we're also going to say that no wave comes from infinity. So the wave we are seeing is just doesn't have any external wave coming from infinity. It's just the wave of the perturbed black hole. And when we set this boundary condition, we get that the frequency omega is a complex frequency. So by this, we get that the oscillation is damped. So when we have a complex frequency, we can write it as a oscillation frequency and a linear, which I call here the oscillation frequency omega, and the linear damping time tau. These frequencies depends on three numbers, which are L, M, and N. The L, M numbers are harmonic indices, and they depend on the angular properties of the black hole. So if it's a black hole, this harmonic indices will be the indices of spherical harmonics, and it's a Kerr black hole. These harmonic indices will be the indices of spheroidal harmonics. And the N index is what we call the overtone index, which is similar to the overtone index of the normal modes. So for every harmonic mode, we can write the gravitational wave as a linear combination of the waves for each normal mode. So we have here the frequency that depends on harmonic ints, and these harmonic ints which are here, and the N index, which is the overtone index. And if we open in terms of a real part and an imaginary part, we have two exponential decayed functions, and we associate this real part with the plus polarization, which and the imaginary part with the cross polarization. This polarization Max told a little bit in the first class. And we also have that this damping time decrease when we increase n. This means that when we have higher overtone, they decrease faster. So the fundamental mode, which is the n equals 0, is the longest living overtone. So and then the first overtone, n equals 1, lives longer than the second overtone, and so on. And I also already told you that this quasi-normal mode frequency depends only on the mass and the spin of the black hole. So if we measure more than one frequency of oscillation and damping time of a black hole merger, we can test the no-hair theorem, which states that a black hole depends only on the mass and the spin, or if you want, the charge of the black hole. And if we measure two frequency of oscillation and damping time, and get that they do not come from the same mass and spin of a black hole, we can conclude that it's not a black hole. It can be some exact object or something else. So how do we measure these modes of oscillation? I want to know if we can measure this mode of oscillation. So to analyze this, we use numerical relativity, because as I told you, the transient part of the ringdown depends on the initial perturbation we give. So the initial perturbation in this case is the merger itself. So we cannot do this analytically. We need numerical relativity to know the initial perturbation, to see if we can see the quasi-normal modes, and see if we can measure more than one overtone, more than one frequency of oscillation. So for the harmonic modes, in this case, in my case, I use the simulation for simulating extreme spacetime with charts SXS. And in this simulation, the harmonic modes are decoupled. This means that we have one wave for each harmonic mode. So they can be analyzed separately. And this has been done by a lot of people. And they showed that the quadrupole moment, which is Lm equals 2, is the dominant mode. This means that the initial amplitude of the wave of this mode is much higher than the other modes. Here in this plot, we can see a plot of the ratio between some higher modes and the quadrupole moment, and we see that the amplitude of the other modes are much lower than the amplitude of the quadrupole moment. And here in x-axis is the ratial mass. For LIGO, we have K equals 1, which are black holes with approximately the same mass. And here you can see it's 0.05, the highest amplitude of some mode. And here they take the overtone n equals 0. So they consider only the fundamental overtone. So we don't expect to see higher harmonic modes in LIGO because of the frequency. They can detect only black holes in this region. And we expect to see them in LISA, because LISA is going to be more sensitive and going to detect higher mass black holes. So we can ask ourselves if we can detect the N modes, more frequency of the overtone modes. But the problem about the overtone mode that they are not decoupled in the simulation. So we don't have a single waveform for each overtone. So for each harmonic mode, we have a waveform which contains all the overtones. So it's a little harder to analyze. A way of doing this is trying to fit a function of the overtone modes into the simulation, into the waveform of the simulation, and see if we can extract the initial amplitude of excitation of these modes. But the problem of doing this is that we don't know when the ringdown starts. So we know that when the quasi-normal mode starts. We know that the first part of the ringdown depends on the initial perturbation, and we don't know when this linear part of the perturbation starts in the simulation. A lot of people ask themselves when the ringdown starts, but most of them neglect the overtone. So basically, they asked when the fundamental mode starts in the case. But there was one paper by Gisler, and which Max is in this paper, where they analyzed the ringdown, consider the overtones, and in their paper they show that the ringdown can start at the peak of the amplitude if they have 7 overtones. So here in this plot we have the amplitude of our gravitational wave, And the ringdown would start here, which is the peak of amplitude, and they could fit 7 overtone. But in our work, we go through a different approach, which we try to consider a more physical way when the overtone starts. So we know that when the overtones decrease faster than the fundamental mode. So there's some time which only the fundamental mode will be there. So because all the other overtones will have decreased. So at some time, the waveform will be the waveform of the fundamental mode only. And we consider that this gonna happen. So our waveform of the simulation is gonna be the fundamental mode waveform when the first overtone amplitude have decay for less than 1% of its initial amplitude. So this is equivalent to a time scale of 5. So when this happens, we consider that our waveform will gonna be just the fundamental mode overtone. And now we try to analyze how we're gonna set the starting time from this. We know that when the waveform is just one overtone, we have that this argument of the complex waveform, the derivative over time. This argument is going to be just the fundamental frequency of oscillation, this frequency here. When you take the derivative of all of this over time, you're going to get just this. And then we see this plot in the numerical simulations. And we see that it approaches the fundamental mode frequency at some time. Here, you can see this black curve is the numerical simulation of this derivative of the complex frequency. And we're going to set this time to be the time which the first overtone have decayed for less than 1% of its initial amplitude. So when the first overtone have decayed 5 scale of time. And then this red curve, vertical line, is this time, when the first overtone have decayed 5 scale of times. This green curve is the value of the fundamental frequency of oscillation. And we set this. If you consider the peak of amplitude, this graph must be shifted to the left. So this red line would be here approximately at 10, I think. Then I shift to the right. So I could set that this time is exactly when the first overtone have decayed 1% of its initial amplitude. And then I can say which initial time by that. I got from a simulation which, like the first detection of the gravitational wave, that the initial time is 10 m. M is the final mass of the black hole. In normal units, this is 3 microseconds. And then after set the initial time of our ringdown, we can see if you can see the fundamental mode. So we fit the fundamental mode. We fit the overtones in our waveform, starting on 10 m, t equals 10 m. And we see if you can see if the amplitudes of each overtone are high enough to be comparable to the fundamental mode amplitude. But when you are fitting function, you have to take some care, because fitting function doesn't mean it's physical. Your fitting value doesn't mean it's physical. So we assume that this result is going to be trustable if they satisfy 2 conditions. First of all, we can fit these functions for the imaginary part and the real part of the wave, which I told you was the plus polarization and the cross polarizations. And our condition is that the amplitude we get for each overtone must be the same for both polarizations. So if you get a different amplitude, means that this problem not physical, because by the mathematics of it, it should be the same. And the second condition we choose is that the value shouldn't vary when we add higher overtone. So when you are adding higher overtone, they shouldn't affect the physics of the wave, but they they are included in the error in the simulation, because the simulation is not has some error, so we cannot. Ideally, we would fit here and to the infinity. So, but the simulation has some error, so we cannot fit everything. So we are saying that if we add another overtone and our values change, it's probably because the overtone isn't there, but we are getting errors in the fitting. By setting these both conditions, only the fundamental mode and the first overtone satisfies this condition, and we get that the ratio between the initial amplitude of the first overtone and the fundamental mode is 3.6. This means that the fundamental mode initial amplitude is higher than the initial amplitude. It means that the overtone initial amplitude is higher than the fundamental initial amplitude. So this means that it is probably measurable, because as we saw in the harmonic modes, the other modes has amplitude much lower than the quadrupole moment. In this case, the fundamental mode does not have the higher initial amplitude. So we can ask ourselves if we can see it in the LIGO observations. An analysis of the quasi-normal mode was already done in the LIGO first detection. But they did not consider the overtones. They only consider here the quadrupole mode and the fundamental mode. And they got that the fundamental mode agreed with the values they got from the analysis of the whole wave when they consider the ringdown start at 10 m, which is exactly the one time I got in my analysis. But here they do not consider the overtone. They associate this here, 1 microsecond after the peak. They associate this not getting equal values with the whole data analysis because of the nonlinear regime. But again, the group from here, Max, made the analysis from the peak, which they did when they made the analysis of the numerical relative waveform, and they showed that when they consider the overtone, the ringdown to start at the peak, and consider one overtone, they would get the values of mass and spin with agreement with the values of the whole waveform of the data. So they showed that when they consider the overtone, they can get a better estimation of the values than just consider the fundamental mode. The yellow curve here is the wave considered the first overtone, and the blue curve, purple, I think, is the values considered just the fundamental overtone at the time 3 microseconds at the peak, and this curve of just one overtone is larger. The error is larger than consider the first overtone in the peak. So I'll finish here. My conclusions are that we can use quasi-normal modes to test general relativity. The overtone of the wave are important. They were considered unimportant for a long time. Most people neglect them, so we conclude that they are important. And we saw that the initial amplitude of excitation of these overtones has a high amplitude, so it's probably that they will be detected before the harmonic modes. And we also saw from the paper from Max that the overtone can help the estimation of the values of the detections made by LIGO. And for future work, we can ask ourselves, what is the best scenario which we can detect overtone? So we saw in the plot of the harmonic modes that the best scenarios were where the ratio of mass of the binary is higher. So we can ask ourselves, this is also true for overtone. And we can ask ourselves, we can use detect overtones in the LIGO and then test the Noether theorem. Because in the paper I showed below, before they didn't consider measuring the modes separately. So they considered the modes came from the same black hole, and then they estimate the values accordingly. That's it.